All right, fantastic. Well, welcome back. Welcome all. It's fantastic to see you. We are GREMax, and we are back here for another installment of our free webinar series with a focus on the quantitative reasoning section, geometry. As a brief reminder or introduction to those of you who are new with us, my name is Jonathan Herzog, head of GRE content here at TestMax. Went to Harvard Law School, went to business school at NYU Stern, undergrad at Harvard. Love the GRE. Have been teaching and tutoring and working in all things GRE for over 5 years. And I'm really passionate about building a team here at TestMax, which is comprised of folks like Daniella. And our entire team is folks who weren't naturals. We had to come to the test, reverse engineer it for ourselves, build from 0 to 1, and really put together the best resources that we didn't have when we were struggling through it ourselves. So with that, Daniella.
Hi, everyone. My name is Daniella. Thank you, Jonathan, for the wonderful introduction. I'm really excited to be here with all of you and together to dive into geometry a little bit more. A little bit about me. I did my undergrad at UC Berkeley and then a master's at Cambridge, and I've been admitted to top 10 law schools using the GRE and PhD programs. I really love the GRE as it's unlocked so many different opportunities for me, and I'm really excited to dive in with all of you today.
Fantastic. So I see some new names here as well. So as always, as you know, or as you may not know yet, we are here for questions and answer, for chat. Introduce yourselves, share your grad school dreams, what you want the GRE to help you unlock. We're here to help support and be of service for you. And with that, our introduction to quantitative reasoning with a focus on geometry. We said these phrases ourselves many a time and hear it many a time from our students. I'm just overthinking. I'm just running out of time. I'm just not a math person. Or particularly applicable for today, I'm just not a geometry person. These are fallacies. We debunk them one by one. You can go to the TestMax YouTube channel and for a general, broader overview of the GRE or our in-depth walkthrough of every other section of the GRE as well. As we know, these are euphemisms for you haven't yet mastered the quantitative reasoning skills sufficient for your target score. The GRE in its entirety is a reading test. The GRE in its entirety is a reasoning test. The GRE in its entirety is a pattern recognition test. We'll see this in play today. We'll dive into real, actual GRE quant geometry questions. And we have a lot of substance and content that we're going to go through at a very high level, not rederive every rule, but just give you a flavor, 30,000 foot taste if you haven't yet dove into it. Or for those of you who already have, a good reminder and refresher on the rules and frameworks and tools in our toolbox. So with that, as a reminder, we're diving into geometry, one of the 4 big substantive areas of quantitative reasoning. And here we go. We always got to pull in some memes or some GIFs to start us off. Meanwhile, in a parallel universe, it just feels so right. 3, 4, 5, magic right triangle. Without geometry, life is pointless. For those of you not rolling on the floor with laughter, we also have some real contemporary reference points for the importance and the relevance of geometry to our lives. We like to ground in our work together. Why are we reviewing basic geometry rules back from middle school or high school, right? Why is that relevant to the graduate school applications process? So just looking at a very tiny subset of examples that are readily available at our fingertips in the everyday, how we get around, right? On Google Maps or Waze, or how we follow the automated navigation apps that tell us where to go, and how we analyze the viral surface geometry to affect the coronavirus spike evolution. So from the pandemic that has wiped out 500,000 lives just here in the United States, to the basic ways we get around in our everyday lives, to even more existential questions in political philosophy and in sociology on what is the meaning of truth and what constitutes mathematical truths. We'll look at this brief quote, again, to just ground ourselves at the utility, at the use of going back to our middle school or high school geometry rules and frameworks, because fundamentally, as this big block quote shares with us, in politics, as an example, perhaps what's true may not matter. Maybe it's what's popular. If something doesn't have a constituency, then maybe it doesn't matter. We might call this political truths. So where's the border? Who's the president? These might be truths you can affect by installing software in people's heads. There's a different school that we might refer to as technical truths. For instance, what is the diameter of this virus in microns? We'll look at diameters today. What is the gravitational constant? It doesn't matter what other people think, it matters what is true. These are technical truths. So again, just heightening our awareness, grounding some of the big, important, even existential questions that emanate from some of the ground truths that we observe in geometry. Okay, with all this lofty, ambitious framing, let's dive into, it's going to be a very high level and rapid overview of these rules, because we've over-delivered and dumped it all for you. So here we go. A straight line, or the distance between 2 points, has a measurement of 180 degrees. Parallel lines, as we saw before, often notated as such, are two lines that never intersect. Perpendicular lines, by contrast, are two lines that intersect at a 90-degree angle. A 90-degree angle is often notated by these little corner boxes on the GRE. Intersecting lines, two or more, as indicated in the diagram here, with angles A, B, C, D, E, and F, angle, again, that measured in degrees, formed by the connection of two particular lines or line segments. We find with intersecting lines, these lines that cross over one another, the sum of all interior angles made by intersecting lines constitutes a circle, or a set of points that are all equidistant, the same distance from a center point. And that has 360 degrees. So you can imagine a circle being drawn. And so all these angles, the sum of them all is 360 degrees. The sum of all interior angles that make a line, recall the line, the distance between 2 points, is 180 degrees. So let's sever this into two. We see angles B plus C plus D constitute this line. Let's call this line B. And indeed, that is 180 degrees. Another term of art, vertical angles. So opposite angles formed by intersecting lines, lines that cross one another, are equal. So in this particular case, we see angle A and angle D. We often notated them with little hash marks or little tick marks to indicate that they are equivalent or congruent or equal. Likewise, with angle B, angle E, angle C, and angle F. So again, we're going to be racing through a lot of rules today. Don't hesitate to stop with any questions. Do not stress whatsoever if this is entirely new or you feel out of the blue. This is intended as an overview for you. All right. Very, very briefly, we'll go through just one of these drills as an example of the type of bottom-up foundational drills work that you'll get used to ad nauseum in our work together. So recall the vertical angles. The angles opposite one another created by intersecting lines are indeed equivalent, demonstrated in the simple case like so. All right. Parallel lines, lines that do not intersect, cut by a transversal, a third intersecting line. So we're introducing many terms of art that may or may not be familiar. Acute, or less than 90 degrees, we can imagine this as a hinge of sorts. a hinge at this 90-degree mark. That brings us all the way down to the 180-degree mark that constitutes the line. All acute or less than 90-degree angles are equal. All obtuse or greater than 90-degree angles are equal for parallel lines cut by a transversal. And any acute plus any obtuse angle is equal to 180. We can rederive this as always, and we go through this together in a bottom-up foundational way. We're just looking at an overview of the rules for today. But let's look at one quick example. So angle A and angle D, we can rederive and prove this to ourselves because angle A and angle D are just vertical angles in the context of, let's call this line A, and the transversal, call it line T. But also, if it's told to me as a constraint that line A is parallel to line B and a transversal line crosses them, then I also know all acute angles are equal. Likewise, their supplementary angles, or the angles for which, when added to that angle equals 180 degrees, are also equal. Again, the double tick marks notating a different pair of angles that are equal. And of course, when we add these two supplementary angles, let's say, for instance, angles A and angle C, we can see that they just constitute a line. So together, they are 180 degrees. The GRE loves to hide things in different types of wrapping paper. We've seen this countless times across all sections of the GRE. Let's take this hidden transversal in a Z. Sometimes, not only are images, particularly shapes when it comes to geometry questions, not necessarily drawn to scale, you cannot make any unwarranted assumptions unless they're explicitly stated, but also there might be incompleteness to the images where inferences might be valid. For instance, if you were to extend this line and extend these lines, and if it were given to you and you were told that these were parallel, you have then recreated, transformed, translated the Z into two parallel lines cut by a transversal where all acute angles are equal and all obtuse angles are equal. Okay, let's clear this and move right along. We've got a lot of different drills, and these are all available to you, but the same principle stands. Just in the interest of time, we'll move on to polygons. Okay, clean slate. Polygons are a closed two-dimensional shape created by these aforementioned line segments, including the familiar triangles, quadrilaterals, and 5+ S-sided polygons. All right, triangles. Triangles have 3 sides and 3 angles. Each here misspelled angle is called a vertex. Each triangle has 3 vertices. 3 sides, 3 angles, 3 vertices. The base is the bottom side of the triangle. The height is perpendicular. Perpendicular is another term of art for saying, as we recall, creates a 90-degree angle width intersecting with the base. The line drawn from the vertex, this point opposite the base, generating a 90-degree angle. The area of a triangle is equal to 1/2 the base times the height. The very familiar, oft drilled into formula, 1/2 the base times the height, and we'll get into the final rule in just a moment in the context of right triangles. Triangles, further rules of the road. Rule 1, the sum of the 3 angles in any triangle will be 180 degrees. Again, we can rederive this looking at triangles in the context of lines, but for now, we're going to posit this. Rule 2, opposite angles will be opposite equal sides. So let's say in this triangle figured here, triangle A, B, and C, we see angle B is equal to angle C. So then this side is going to be equal to that side. Rule 2b, the largest angle will be opposite the largest side. And another corollary, rule 2c, the smallest angle will be opposite the smallest side. So there is a relationship between the angles and the sides created. We can always resort to intuition and basic line drawing. If we go back to our original hinge, right, we have this 180-degree line, if we, hey, take this small angle, or hey, take this 90-degree angle, or hey, take this bigger angle, you got to complete the third side of the triangle, right? So think about the sides of the side. You have a small angle, a bigger angle, and the largest angle. What's the size of the side that you need to close the third side? Smaller, bigger, biggest. We can always rederive the rules if they're not readily available in our minds. Rule 3, the sum of any two sides of a triangle must be greater than the third. And corollary, if you know two sides of the triangle, the third must be greater than the difference and less than the sum of the two. This one can get a little bit confusing, but let's write it out as an expression. So we have 3 line segments. Line segment X, Y, and Z. Again, using our hinge model, our hinge analysis, we're trying to connect 3 different line segments so that we create our 3-sided triangle. In this case, what rules 3 and 3b are telling us is that side 3, or side Z, must be greater than the difference, X minus Y, and less than the sum, X plus Y. For now, again, we're going to posit this, but we can always rederive. Right triangle rules. Rule number 1 of right triangles. A right triangle has one right angle, that famous 90-degree corner. Rule number 2, a right triangle has 2 legs, legs A and B, and a hypotenuse we call C. The hypotenuse, rule 2b, is opposite that right angle. That right angle, that is the only right angle in the right triangle. So we can call this C, we can call this A, we can call this B. The very beautiful and centerpiece theorem, the Pythagorean theorem, a squared plus b squared equals c squared. We know legs are A and B, and C is the hypotenuse. So for right triangles, we'll see a number of examples in just a few moments. The square of the length of the first A plus the square of the length of the second leg B is equal to the square of the length of the hypotenuse C. We have 2 very, very special VIP right triangles. We'll see just a little bit more about them in a moment. The 45, 45, 90 and the 30, 60, 90. 45, 45, 90, the isosceles right triangles. Isosceles where 2 of the sides are equal. The relationship between the legs and the hypotenuse goes as follows: x, x, and x rad 2. Recall integrating our previous rules of triangles. Note the relationship between the sides and the angles. 45 degrees corresponds to x, 45 degrees corresponds to x, equal angles, opposite equal sides, and the biggest angle, the largest angle, the 90-degree angle, the right triangle corresponds to the largest sides, radical 2 times x. So we also have the very special VIP triangle, the 30, 60, 90 triangle. Recall again, of course, as always, all angles in the triangle must add up to 180 degrees. In this case, again, the length of the legs corresponds to the size of the angles. Our x are the relationship between the size of the legs and the hypotenuse goes as follows: x, x rad 3, and 2x. Of course, we drilled through this in a very bottom-up foundational way. We can tend to approximate. Rad 2 is 1.4, rad 3 is 1.7. In any case, it's a multiple greater than 1, so it's bigger than x. Again, we can rederive this all ourselves. We see 30 is opposite the side x, 60 is opposite the side, that's approximately 1.7 times that, and 90, the largest angle, the right angle, is opposite 2 times that. These relationships will appear over and over and over again. We love our VIP right triangles. All right, so we have many derivations, and if you may recall from grade school, cutting up pieces of paper or using pieces of yarn, using protractors or rulers or lots of different mechanisms to prove this empirical or natural reality. This just happens to be one of them, demonstrating the Pythagorean theorem. If we take a 3, 4, 5 right triangle, we take leg side 3, and we square it. We go back to our exponents lesson, which is posted on our YouTube channel, very helpful for this. We have 3 rows of 3, that gives us 9. Leg B is a 4. We have 4 rows of 4, that gives us 16. And indeed, we find, again, this being one of our technical truths, that 9 plus 16 is 25, which is equal to the hypotenuse, or side C, squared. So indeed, it works. All right, we have our frequent flyers. Again, the GRE loves wrapping paper. It's a reasoning test. It's not a math test. It's a reasoning test that uses the language, logic, and syntax of mathematics and of the English language. The way reasoning tests can have very predictive, statistically valid tests is by giving you frequent flyers packaged in different ways. So what we originally had is our 3, 4, 5 triangle. We can multiply every side by 2, multiply every side by 3, multiply every side by 4, and that gives us 6, 8, 10, 9, 12, 15, and so on. The relationship being leg, leg, hypotenuse. I saw there might have been a question. If a triangle with a box in the corner indicating a triangle is a right triangle, but the directions don't include that information, can I assume that the box means it is indeed a right angle? Phenomenal question. The answer is yes. However, what you cannot do, and what the GRE loves to prey on, is there not being that little box in the corner and you assuming, hey, it kind of looks like a right triangle. Nope, that's not valid. We need that little box. Otherwise, that inference is unwarranted. Great question. All right, so we saw our 3, 4, 5 triangle. And again, you might get packaged the wrapping paper of the day on the day you show up to the test is a 6, 8, 10. But you have that dexterity and you say, hey, I'm translating it to what I know. Break it down, translate it to what you know. It's always going to be the same. Likewise for 5, 12, 13, and 8, 15, 17. You can always rederive and prove this to yourself that indeed a squared plus b squared is equal to c squared, c being that hypotenuse, right, in our right triangle. But these are very frequent flyers and helpful patterns to recall. 3, 4, 5, 5, 12, 13, 8, 15, and 17. All right. We alluded to this just a moment ago with VIP special triangle number 1. Let's dive a little bit deeper. Again, I know there's a lot of content today, and trust me, there's even more. So do not stress, do not worry. This is just, imagine you're gliding in a plane, looking over the field, just getting a glimpse at what's to come, or a nice refresher if you've already been in the weeds. So recall, terms of art, isosceles triangles, just as we do in the verbal reasoning section, we translate, we break down, we turn it into simple English. Okay, 2 of the 3 sides are of equal length. Cool, got it. Recall, integrating our rules, the angles opposite those 2 sides are also equal. So even if you didn't know that, you could re-derive it. An isosceles right triangle is exactly what it sounds like. It's an isosceles triangle where 2 sides are of equal length. And we have one right angle. But hold on. The other 2 sides are equal, so those other 2 angles are equal. And so we're basically told we have 90 plus 2 times x is equal to 180. So indeed, the other 2 angles are 45 degrees. You can always rederive it for yourself. As we saw, the legs of an IRT, or an isosceles right triangle, will be always in the following ratio: x, x, x grad 2. Substitute any value for that you'd like. A fun little fact is that an IRT is half of a square. We'll get to a square in just a moment. But when you put together 2 isosceles right triangles, you get a square where all 4 sides are equal and all 4 angles are 90 degrees. It turns out, again, the GRE loves this because it loves the wrapping paper. if you know the diagonal of the square, you can find the side. The diagonal, when you put these two triangles together, is going to be the side times the square root of 2, because it's composed of two isosceles right triangles. So as you can see, there aren't even that many rules, aren't even that many frameworks, but they just get repackaged and repurposed in lots of different ways to make it seem like it's something new, but it's not. Okay, so that was VIP special triangle, right triangle number 1. VIP special triangle, right triangle number 2 was our 30, 60, 90. Okay, equilateral triangles, we can infer this, use some of our vocabulary inferences, equal, has 3 equal sides and 3 corresponding equal angles. 3 equal angles, a triangle has 180 degrees, each therefore is 60. So as it turns out, if we introduce a bisector, or a line that cuts another line, it meets in a perpendicular fashion, 90 degrees, but it cuts the other line into 2 equal portions, we can split an equilateral triangle where all 3 sides are equal into 2 30, 60, 90 triangles. This is the definition of a bisector. It's a perpendicular bisector. It cuts this side into 2, so it creates 2 90-degree angles. We know the equilateral triangle has 3 60-degree angles, and this bisector is cutting this angle into half, so 60 divided by 2 is 30. So voila, we've created a 30, 60, 90 triangle. As we recall from special VIP triangle, right triangle number 2, the relationship between the legs that the GRE loves to test is x rad 3, or approximately 1.7 times x, and 2 times x. The largest side, the hypotenuse, opposite the largest angle, which is indeed 90 degrees. Okay. Another question? No, same one. Brief sip of water as we go on to exterior angles. Note, again, we can rederive this using the same basic foundational rules, but it's useful to have as top of mind. Again, we're just storing this away in another tool in our toolbox. Okay, an exterior angle is equal to the sum of the 2 opposite interior angles. So here we have triangle, let's call it ABC. We have this exterior angle D. Again, this may or may not be drawn for you in such a visually apparent way. However, let's pause it. The exterior angle D, let's extend this line a little bit further, is equal to the sum of the 2 opposite interior angles in the triangle. So we can prove this to ourselves a million different ways, but let's look at the easiest. D and C are supplementary, so together they add to 180, right? So whatever's here plus whatever's here is equal to 180, because 180 is a line. Hold on, whatever is here, angle C, plus whatever is here is equal to 180, because that's how many degrees are in a triangle. So without even doing any math, which is the best way to approach the quant section, don't do computation, do quantitative reasoning. Hey, this has got to equal that. Again, we can rederive it and prove it to ourselves with transversals, with intersecting lines, with definitions of the angles and lines and triangles. But for now, let's pause it. The exterior angle is equal to the sum of the 2 opposite interior angles in a triangle. Again, always another tool in our toolbox, in a strategy tool, is, hey, you don't have to, you can draw in, just like we saw in that Z, you can draw in imaginary extensions, provided you're not violating any constraints or making any unwarranted assumptions, like it's a right triangle, let's say. But so long as you're not violating any rules and you're abiding by the constraints, if this helps you visualize, oh, whoa, I've got 2 parallel lines intersected by a transversal, in this case, the question might depict it exactly like that. You might not even see the triangle, or you might not see the exterior angle, but in a pattern recognition way, hey, if I create something where I have a triangle every vertex, every side of the triangle is going to have some exterior angle if I extend this line, right? Some exterior angle if I extend this line, and so on and so forth. Okay, very briefly on similar triangles because they're not as commonly tested, but an important concept to know nonetheless. Similar triangles refer to triangles that have a similar or the same shape, but not necessarily the same size. What this means is the corresponding angles are equal, whereas the corresponding sides are in the same ratio. Note, these types of questions will often, in the rare case they're asked, involve you perhaps flipping things in your mind. This is where you can make a lot of mistakes, so I would suggest redrawing it to make it easier. So for instance, if we're told that angle y is equal to angle y, angle z is equal to angle z, angle x is equal to angle x, it's super, super easy. You know there's trap answers waiting if you want to somehow relate or say these sides are in proportion, just because that's how they're given to you. But hold on, z and x here are flipped, right? X is on the left side here, it's on the right side here. So you might want to redraw it for yourself, carefully notating as if we're flipping a mirror image, carefully notating the angles as well as the sides. This will allow us to find and confirm that indeed the corresponding sides are of the same ratio, or they are proportional, or one divided by the other is equal to the other divided by the other. Okay. We're racing through it. Recall, a polygon is a closed two-dimensional shape created by line segments, including triangles, quadrilaterals, and 5+ s-sided polygons. Quadrilaterals, 4-sided polygons, most commonly include, on the GRE, parallelograms, rectangles, squares, and trapezoids. Parallelograms, equal parallel opposite sides and opposite angles. Rectangles, parallelograms where all angles are 90 degrees and opposite sides are equal. Squares are rectangles, so all angles are 90 degrees, but all sides are also equal. And trapezoids have one pair, quadrilateral where there is one pair of parallel opposite sides. A brief overview of a rule that you may get possibly 1 out of the 40 questions of the quant section on, if at all, is the sum of the interior angles of a polygon, which can be broken down into its constituent triangular components. So we find that the sum of interior angles of a polygon, now of course, as always, sometimes you may need to extend lines to visualize it for yourself. You may need to imagine a particular exterior angle relationship to rederive the familiar image. But here we're looking at a hexagon, 6 equal-sided polygon. And so the sum of the interior angles we see here, a hexagon placed inside of a circle, so as to be easily divided into 6 equal triangles. And we find that the sum of the interior angles is equal to the sides n-2 times 180 degrees, the number of degrees inside of a triangle. Indeed, any quadrilateral can be split into 2 triangles by a line connecting opposite corners or vertices. All right. Perimeter and area all in one. Perimeter, distance around the polygon, the sum of all of the sides. Again, sometimes you'll have to draw in or infer what's being asked for as it relates to the perimeter. Area is the space inside of the polygon measured in units squared. Why unit squared? Because let's say we have our square with each side being 3 inches, the area is going to be one side times the other. Square has 4 90-degree angles, equal opposite sides that are all parallel. All sides are equal, so it is merely 9 inches squared. Area of a rectangle more generally is length times width. Let's say we have 4 feet times 5 feet. Area is equal to 20 feet squared. Area of a trapezoid, we have one set of parallel opposite sides, is going to be very similarly to our area of a triangle, and often presented in the following way: 1/2 base 1 plus base 2, or a plus b over 2, times the height. Recall, the height is the line that is perpendicular on the opposite side to the base. It creates a 90-degree angle with the base. Again, sometimes you'll have to draw that in yourself. It may or may not be given. Area of a parallelogram, 2 pairs of parallel equal sides is simply base times height. Note again, in a quadrilateral, we can create lots of different triangles, either by connecting vertices or endpoints, or by drawing the height or the line perpendicular from the opposite side to the base. Base times height, base 1 plus base 2 over 2, or a plus b over 2 times height. Circles. Circles. The set of points equidistant from a fixed center point. Now, going back to the previous question, you cannot assume it's a right angle unless you see that little box or it's told to you. Likewise, you cannot assume that a dot in a circle is the center point unless it's clearly indicated as the center point. Set of points equidistant from a fixed center point has a total of 360 degrees. The radius is the line segment connecting the center point to a point on the circle. Chord is a line segment connecting any 2 points on the circle. Diameter is a chord that passes through the center of the circle. It turns out that diameter is equal to 2 times the radius. How do you know this without just knowing it? Is that, hey, the definition of the circle is the set of points. If we recall using our protractor from grade school, the set of points that are equidistant from the center. So r plus r, 2r is equal to d, the diameter, a chord that passes through the center of the circle. Okay, this is a very fundamental relationship. The Archimedean constant pi, or 3.14 ... a rational number, often approximated in calculations as 22/7, or some value greater than 3, a useful shortcut sometimes for our quantitative comparison questions. Circumference C, the distance around that circle, right, that set of points equidistant from a center point, is equal to our very famous 2 pi r, or pi d. Having flexibility in translating between the diameter and the radius is so fundamental to any circle question. You are most likely to see it on test day. Recall that diameter d, the distance across the circle, the chord that goes through the center point, is 2r. Radius r, half the distance across the circle, 1/2 d. Again, we're just having dexterity in relating the diameter and the radius and the area of the circle. The very famous pi r squared. You know the radius, you know the rest. Central and inscribed angles. Central angle is the angle that has the vertex at the center of the circle. The inscribed angle has a vertex on the circle. It can be at any point on the circle. An arc is some portion of the circumference. A sector is some portion of the area of the circle. It turns out an inscribed angle is going to be half of the equivalent central angle. Let's say I can't assume just because it looks like it, but let's say I know this is a right angle, 90 degrees. I know the inscribed angle is half of that. Likewise, because of the relationships with the angles, the area of the corresponding sector, right? So this being the arc, this being the sector or the part of the area of the circle, is going to be equal to the ratio of that angle, that central angle over 360 degrees, times the area of the circle, which is that pi r squared. So sometimes we're asked about an area, again, of a particular sector, particular area of a circle. We find that by taking the ratio of that angle times pi r squared. Inscribed triangles. Inscribed triangles, all vertices are on points of the circle. All 3 points are on points of the circle. If one side of an inscribed triangle is the diameter, the chord that goes through the center point of the circle, then it must be a right triangle. How can you prove this to yourself? Well, combining the rules that we just saw, which is the inscribed angle is going to be half of the central angle. In this case, we have a semicircle, right? A semicircle is half of a circle, so this has 180 degrees. Here, the inscribed angle corresponds to the same arc, the same half of the circle, semicircle, and so it's going to be half of that measurement. Half of 180 is going to be 90, so we have a right triangle. A very powerful inference the GRE loves. By corollary, if you have a right triangle and it's inscribed in a circle, as may be given to you, then the diameter must be one of its sides. Therefore, again, it cuts the circle in half, and we have a semicircle. Again, we can use the same rule with the inscribed and central angles, which is, hey, we have some angle at a point on the circle. In this case, we know that it is going to be half the measurement of a semicircle, which is 180 degrees. In this case, it is indeed a right angle. All right. We're going to skip over three-dimensional shapes for today, so we can just glance at some of the fun that we'll have in the future. Cubes, rectangular solids, cylinders and volume, surface areas, and all the like. Really, we're just integrating the same stuff we did with two-dimensional shapes, but just making broader inferences to three-dimensional shapes. Same basics. And we're going to quickly look at the coordinate plane before diving into real GRE quant questions. All right. Coordinate plane. We have a horizontal x-axis and a vertical y-axis. These axes are perpendicular, creating these right angles everywhere. They intersect at the origin, or the point 0, 0. The origin, the intersection point of the x and y axes. The x-coordinate is the first number in the ordered pair, identifying a point in this two-dimensional plane, x, comma, y. So 2, comma 3 on the x-axis. Positive numbers go this way, so this would be 1, 2. On the y-axis, positive numbers go this way. This would be 1, 2, 3. So if I'm given x, y coordinate 2, 3, I'm going to go 2 to the right and 3 up, and I've arrived at point 2, 3. The y coordinate is indeed the second number in this ordered pair. The origin point 0, 0, where the axes intersect. The x-axis is where y is equal to 0. The y-axis is where x is equal to 0. And we'll see indeed today, the GRE loves to look at lines or different points in and around the coordinate plane. We call these quadrants. Quadrants are created by the intersection of the x and y axis. Quadrant 1, x and y are positive. Quadrant 2, quadrant 3, and quadrant 4. So you can infer for yourselves, but as you know, positive, negative, positive, negative. So the quadrants go counterclockwise. All right. Slope, a very powerful tool in our coordinate plane and our coordinate geometry, is presented in lots of different ways. You recall from grade school, rise over run, delta y over delta x, the change in y over the change in x, presented also in point slope form. So y2 minus y1 over x2 minus x1, always making sure that we're pulling from the correct points. Let's look at this example. We have a point in the coordinate plane. Again, imagine and think back to our original, like, why the heck are we doing this again to get into grad school? Oh yeah, because like, as an example, this is how we get around. This is how we like move throughout the world. So like, we're at point 1, 2. You can think latitude and longitude when you get more complex. But here in the coordinate plane, you're at point 1, 2. You want to get to point 4, 3. So like, how does Google Maps, or how is it telling you to get there? Well, if we're looking at the slope of the line, or the distance between these 2 points, we're going to, we can go either direction. So we're going to rise, we're going to go up 1 on the y-axis, and we're going to run horizontally 1, 2, 3 points on the x-axis. And indeed, our x-y coordinate, we know x comes first, y comes second. That is reflected in our calculation of the slope, the change in y over the change in x. The change in y, in this case, is y2 minus y1, which is 1. Change in x is 4 minus 1, which is 3. That gives us the slope of 1/3. Very commonly tested is the slope by reference, the slope of, say, 1. So let's say we have the origin 0, 0. A slope of 1 looks like a straight line through the origin that goes to the points 1, 1, 10, 10, where the change in y is exactly equal to the change in x, a straight line with a slope of 1 through the origin. 4 types of slope: positive, up and to the right; negative, down and to the right; 0, like the x-axis; undefined, like the y-axis, because you can't divide by 0. Intercepts: points where a line intersects or crosses an axis. Again, recall the x-intercept where y equals 0, the y-intercept where x is equal to 0, also presented as the xy ordered pair. Okay. Again, the GRE loves wrapping paper. We have all the fundamentals, but if we present them in a different way, it makes it easier to see. So the GRE will not give you that low-hanging fruit, but ask you implicitly to represent it. Y is equal to mx plus b. M is that slope, that change in y, or delta y over delta x, the rise over the run. The b is that y-intercept, that point where x equals 0, where it crosses the y-axis. A very, very strongly tested skill is our ability to rewrite linear equations or representation of lines from ax plus by equals c into slope-intercept form, which again, we have the slope and we have the point at which it crosses the y-axis. All right. We can integrate all of the abundance of rules we have together to use and determine the distance between 2 points. Note that we can draw a right triangle and use the Pythagorean theorem sometimes, while we want to avoid computation, but another tool in our toolbox to find the distance between 2 points. Okay. 30,000-foot overview of the tools in our toolbox as they pertain to geometry. Now being applied to real actual GRE quant comparison questions focused on geometry. Quant comparison, we're looking at two different quantities, the emphasis not being, hey, crunch the numbers, but hey, do the reasoning. Choice A is always bigger, B is always bigger, C, they're equal, D, I don't know. Daniella.
Thanks, Jonathan. Hi, everyone. I'm going to take you through a few questions, and then I'll hand it back to Jonathan for a couple more questions, and then he will conclude our session today. So let's jump right in. So what we see here are two different triangles. One on the right has a right, both of them have right angles. One has a 4 and a 4. And what does this remind us of? This reminds us of the framework that we learned before of the x root 2 right triangle. So here, to fill in that pattern, we know that quantity B has to equal x root 2, which is, in this case, 4 root 2. Now, if we were to look at the other triangle, what framework does that bring up for us? Well, it reminds us of the triangle that looks like this, which is x, 2x, x root 3. So that means that x here, which is this x here, is x root 3, and in this case, 4 root 3. And now we're comparing these two quantities, 4 root 2 and 4 root 3. And usually on typical GRE webinars, I don't usually dive into the frameworks immediately. I usually ask a question beforehand. Is D in play? Does the answer exist? And because we saw these two frameworks, we knew that D was in play, that D, we can solve for X and Y, we can solve for quantity A, we can solve for quantity B. So the relationship cannot be determined from the information given is no longer in play. And also, going back to the answer choices, if we're comparing 4 root 3 to 4 root 2, we know that the square root of 3 is greater than the square root of 2, and therefore A is the correct answer. Let's say we forgot. Let's take a second here. I know we're short on time, but let's take a second here, and let's say we forgot this framework here. We forgot what this looks like. What could we do? If we remember the x root 2, but we forgot the other one, it's okay. We could use the Pythagorean theorem and solve and go 4 squared plus b squared equals 8 squared. 16 plus b squared equals 64. Subtract 16 from both sides. B squared equals 48. I'm just continuing up here. And then you can break down the square root of 48, and that ultimately becomes 4 root 3. So with that, I'm going to clear, and we can move on to our next example.
Fantastic. I love it. One quick note, just going back to the previous question, is note all the power that Daniella unlocked there, integrating all of our rules and frameworks, were because, as the questioner noted, we're told that they're right triangles. No one said, hey, this is a right triangle, but this is screaming out at us, hey, pull out the tools in your toolbox that relate to right triangles.
Moving on to the next question, we're just going to actually do some general observations up front. So what do we see here? We see a circle and a triangle that's inscribed into that circle, and we have a statement. And what does that statement say? O is the center of the circle, and the perimeter of triangle OAB is 6. Okay. Quantity A says the circumference of the circle. Okay, what's the formula for circumference? I'm just going to jot that down quickly. It's 2 pi r. And the quantity B is 12. They're asking us, okay, the only unknown here is the radius, and we have the perimeter. So let's say if we can solve for it. We think that D is out of play, in other words, that we potentially could solve it, and we can determine the relationship between quantity and quantity B. So let's try to do that. So what do we notice here? Because O is the center of the circle, what does that mean about OA? OA here, I'm just gonna, which is this, and OB. It means that OA and OB are radii of the circle. And what does a radius mean? It means that they're equidistant. And what does that mean? It means if the lines, these little tick marks, show the fact that these two sides of the triangle are equal, it means that their angles here are equal. Here, let me just make that a little bit more clear. So if the sides are equal, it means that the angles are equal. And we know that the sides are equal because we know that O is the center of the circle, and that means that OA and OB are radii of the triangle. And we know that one angle is equal to 60 degrees. Can we assume that angle OAB, this angle, and OBA are equal? Yes, we can assume that because their sides are equal. So let's try to find out what these two angles, let's just call them X for now, are. So we have, and we know that the total amount of degrees in a triangle is 180. So 180, which is the total degrees of the triangle, equals 2x minus 60. Sorry, plus 60. And if we solve for that, we learn that x is equal to 60. And that means that this triangle here is an equilateral triangle. So if we were to just draw this triangle out on the side, 60, 60, 60, with these 2 points being on the larger circle. And we also, and O here being the center of the circle. And that also means that we have, if the perimeter here is 6, that means it's an equilateral triangle, we know that each side is 2. So if we're solving for the circumference of the triangle, we take the radius, which is 2. So we know that that's equal to 2 times pi times the radius, which is 4 pi. And 12, to answer the question, is, if we broke that down, it's 4 times 3. And what is 4 times 3? And pi is equal to 3.14, which we know is greater than 3. So therefore, we can assume that 4 pi is greater than 4 times 3, and therefore quantity A is greater.
Phenomenal. 2 quick high-level observations, or rather 3. 1, notice how Daniella pulled in, like, boom, all of our rules, triangles, circles, and the inferences combined to unlock inference after inference after inference. Key point number 1, right? So notice all the wrapping paper around all the fundamental rules we just talked through. Observation number 2 is note that very little, if any, math or number crunching was done. Danielle was not calculating. She's not punching into her calculator 4 times pi. Because the GRE, again, is a reasoning test. It's not a mere math test. We're looking at comparisons, relationship, pattern recognition, breaking down, translate it, turn it into what you know. 4 pi, oh, wait, 12, break it down, 4 times 3. Oh, I see a 4. Oh, I'm actually just comparing pi and 3. Oh, pi is bigger than 3. Oh, I don't even have to figure it out. Quantity A is bigger. So it's a resource allocation test. The GRE will punish you heavily if you have ego. We all have ego, but the GRE will punish you heavily if you have to prove yourself. Aha, I can do long division. Aha, I can do this complicated multiplication. So what? The GRE is a resource allocation test. Daniella says we can get to choice A in, hey, 45 seconds and not even do the math.
Okay, so let's look at our next question. A couple of observations up front. We have a question, and we don't have choices A, B, C, or D, where D doesn't means that you can't tell the relationship between A and B. It's not a multiple choice question. Here we have a bunch of different questions here, which means that multiple of these answer choices could potentially be correct. And that's differentiated on the GRE by having a square answer choice versus a circle or oval answer choice. So now let's look at the question itself. In the triangle ABC, the measure of angle A is 25, and the measure of angle B is greater than 90 degrees. Which of the following could be the measure of angle C? Okay, so let's take a look at this question, where we have one angle here that's 25 degrees. We're going to just sort of draw it out. So let's say this angle here is 25. And that's angle A. And we have angle C, but we just know that angle B is greater than 90. So we know that this angle is, so let's look at what a 90-degree angle would be, is here. But we know that this angle could look like this. We know this angle could potentially look like this. We know that this angle could potentially look like this. It could be anything that's even a smidgen greater than 90. So we don't really know exactly where this angle is going to be. So which of the following could be the measure of angle C? Okay, so we have 180. So let's see what we have here. So we know that the total number of degrees in a triangle is 180, okay? Now we're going to take away the degrees that we know already, that are going to already be taken during this triangle to create this triangle. So we know we already have an angle that is equal to 25. So we're going to take that away from the total amount of degrees. And remember here, we're solving for the measure of angle C. So we're trying to figure out which of these angles here, which of the following of these measurements, A, B, C, D, and E, could be the measure of angle C. So we're taking away 25 because that's taking away from the total. Also, we know it's greater than 90. So we're going to take away 90 degrees. And that leaves us with 65 degrees left over to divide between this 90+ degree angle, let's call it angle B, and angle C, which is this mystery angle over here. So let's say it's a little bit greater than 90. We're going to finish up our triangle. So we have 65 degrees to divide between those two angles. And so now let's look at our answer choices. Can angle C be 70 degrees? Because if we only have 65 degrees left, then angle C can't be 70 degrees because then our triangle would equal over 180. Because let's just look at this for a second. So if we take the minimum possible value, which is, let's say 90.000 all the way to 0.1, like 0.0000000, an infinite amount of zeros repeating with a 1 at the end, then we added that to the 25 that we already have, and then we added 70 more, that would be over 180 degrees. That would be greater than 180 because the maximum that we could potentially have is 65. And because the maximum we potentially could have is 65, A works, B works, C works, and D works, but E is not the correct answer. So just to be a little bit more clear, I'm just going to erase this. And those are our correct answers. Jonathan, do you have anything to add here?
Fantastic. All right. So in the interest of time and the protection of your evenings, we will make sure we get ourselves to the end. These are all available for free online. So no stress, no worries. We'll finish it off with a fun coordinate geometry question and then wrap up. Okay. We have a coordinate plane, XY axis. We have a line K. We have a point 3, 4, an XY coordinate 3, 4. And it goes through the origin. Whoa, super powerful. Okay. Quantity A is the slope of line K. I don't know what that is, but okay. Quantity B is 1. Okay. So we're comparing the slope to 1. I wonder what the slope of 1 would look like. Okay. So the origin, which is the point 0, 0. We said a slope of 1 is where like the change of y is equal to the change of x. So it's this line that goes to the origin and goes to the point 1, 1, 2, 2, 3, 3. Right? It's the line where the change in y would be 3 minus 0. The change in x would be 3 minus 0. So we get a slope of 1. Okay, so that's what a line of slope of 1 would look like. Wait, okay, this point's even higher than that. Wait, this line's even steeper than that. So the slope is going to be bigger. I don't even have to figure out what the heck it is. Lots of different ways to get to Rome. As always with the GRE, you could calculate the slope of this line using this point, and again, see that regardless of what that slope is, this line slope is going to be greater. It's going to be more positive. It's steeper. It's harder to get up that hill. Or you could compare it to that line of slope 1. Either way, quantity A is greater. Again, notice I didn't calculate the slope of line K. I just considered it in relation to using the breadcrumbs I'm asked to call upon the pieces of information that I know. Critically, the fact that this goes through the origin and it's on the XY coordinate plane, and that I'm given by comparison either this point 3, 4, by which I can calculate a slope, the change in y over the change in x, or even just use quantity B, cheat off of B, and see that quantity A is bigger. So with this, take a free practice test online, if you haven't already, find your minimum baseline, download the GREMax app on tablet mobile, sign up for a free 20-minute consult with a GREMax team member. We're more than happy, as always, to stay on even after this call to answer any of your questions, thoughts, reflections. With that, many, many, many 5-star reviews, but thank you, thank you, thank you. We're here for you. Please ask us any questions, thoughts, reflections, and have a wonderful evening. Oh, fantastic. Thank you so much. All right. Well, barring that, don't hesitate to reach out at any point. We're here for you. Have a wonderful evening and take care. Thanks for joining us.